quantum physics and maths, which I promised to spare you. So I think today I'll hopefully give a sort of semi-light-hearted, but beginning to be a little bit of a deep dive into quantum computing. And I think the title of the talk was the reality behind the hype. And so hopefully I'll describe to you a little bit about the promise, so why people are starting to get interested in quantum computing. But then also, and I think particularly this will resonate for you as engineers, I'll give some more practical, tangible examples of what's really happening. And you'll hopefully come to understand that a lot of those challenges are very related to engineering, sort of quality control and electronic control and things like that. So good. So can you introduce me a little bit? So my background is quite varied. So I do have a PhD from Southampton a long time ago in quantum optics, and after that point, pretty much immediately learned that I wanted to leave academia and exploit, get into product design using scientific principles. So I went and joined a consultancy called TTP based in Cambridgeshire that you might know about. And my job there was sort of to take a lot of emerging science and optics and turn those into tangible products for different customers. So I like to say involved in lots of exciting projects. I developed novel nanostructured coatings for Oakley. So one client was Oakley for a little while. I did some nanostructured coatings, in this case, to help the fluid flow around Boeing aircraft. So Boeing helped them develop the film technology that applied to the outside of aircraft, and lots on imaging technologies and other things like this. And then, as Keenan described, went on to work for UK government, or an arm of UK government, right at the early stages of quantum technology. So right at the point where there was lots of academic activity, and increasingly people were starting, and government was starting to become more aware that quantum was more than just a scientific discipline, and it could be applied to new products. So I led the government initiative starting in 2013, and in total that was a £270 million stimulus package into quantum companies that I then led from 2013 to 2017. Became familiar with lots of academics, lots of companies in that space, and one company was an Essex-based company. So E2V, or now Teledyne E2V, were really doing a lot of good work in there. So after I left government, I went and worked for Teledyne E2V and met Trevor Cross, who I think was the person who suggested that I give this talk. And then, in that time, met a lot of very good academics, and in 2019, November 2019, myself and a few academics got together and started Orca Computing. So I'll go into more details in a little bit on what Orca's doing. But the nutshell is, it's quantum computing, but our approach is quite novel and trying to use single photons, so single units of light, in order to do computing and quantum computing. And it's quite an interesting sort of journey that we'll go on, that hopefully I'll describe to you. So I should say before we get started, I am keen for this to try and be informal. I should admit, I've given a lot of Zoom talks since lockdown, but this is my first talk where I'm trying to be as informal as possible. So if at one point you would like to interrupt with a question, then please do. That might make me feel a little bit less like I'm sitting in a room on my own, giving a presentation to a computer screen. So if you do want to ask questions, please, I'm more than happy for you to do that. Otherwise, look forward to answering your questions at the end. So what is quantum computing? Why is it so interesting? So there was a really nice quote some years back by Bill Phillips, who's a Nobel Prize winning physicist, who said, "Quantum computing is as different from classical computing as a classical computer is from an abacus." So what he was trying to say there is, if you're thinking of a quantum computer as a slightly faster, slightly larger computer, then in fact that's not the case. So quantum computing is almost a redefinition of how people currently think about computing. And in that lies part of the challenge that I hopefully described to you. So imagine not just sort of coding a system as you would a normal computer, but needing to take a whole new approach towards what you think of computing, needing to take a whole new approach towards programming, or even relearning what you think programming looks like, and really completely redefining the whole supply chain and logistical aspects around current computing. And if hopefully that helps you describe, understand why certain government players, and it is a well-backed government activity, UK government activity at the moment. UK government and several other governments around the world really are seeing this as an opportunity for countries like the UK, who maybe arguably might have missed out slightly on the classical computing industry. It gives sort of us an opportunity, probably like no other, to grow a completely new industry and supply chain and all of the applications and benefits that come with that for the UK. So that's the opportunity that I'll describe in a little bit more. Obviously, that huge opportunity does come with some challenges and difficulties. So this isn't easy. This isn't totally straightforward. I think many of you might take a look at what's being suggested here and think that it's very early stage. You know, I've had comments that have said to me before that this is just blue sky research. This is just, you know, very abstract. It's never going to go anywhere. It is quite blue sky, but it is also very focused around delivering new computing systems. So, and there's, by the way, a lot of money being put into it by several major players like Google. And so I like to sort of challenge people when they say, oh, it's blue skies, it's never going to do anything, and say, well, actually, the market opportunity is so large and the opportunity for investment from the private sector is so large that actually really huge breakthroughs can happen. And it's very analogous to, you know, the previous breakthrough, which, by the way, the UK led, of course, you know, coming out of the good work in around Milton Keynes. Yeah, the UK has led on revolutions in quantum computing before, and we can do it again. So I think the scale of the scientific challenge is not insurmountable. It's just hard. And I think, and of course, as I said before, engineering is really going to come into the foreground as being incredibly important to see these systems through to real and useful devices. So many of you may already be familiar with sort of quantum computing. You may have seen some of these sort of nice shiny pictures that are published by all of the leading players. So the machine right in front in the center of your screen is a machine that's being built by IBM. And the machine on the top left there is the one built by Google. And then sort of bottom left is something, if you've ever seen the BBC program Devs. So that was a lot of sort of nice sort of visualization about what quantum computing could look like. And then another sort of slightly different version, which maybe engineers might appreciate a bit more, sort of just a big black box. So you don't really need to worry about what's on the inside. It just works. So what's interesting with these things is, you know, most of these pictures, by the way, are not really showing you the computing element. So these systems are in fact very large refrigerators, very large cryogenic coolers, which bring the temperature down. So there are various different stages. At each stage, you lower the temperature and until you get to the very bottom of the device, where you have something at several degrees above absolute zero. And in that very small part at the bottom, you have a little chip in which the quantum stuff happens, which I'll talk about later. So that's what it looks like. But if, like my wife, you look at these things and sort of go, well, hang on a minute, that doesn't look anything like a computer. So my wife's comment upon seeing one of these pictures was, that's not a computer. Where's the keyboard? So, you know, there is a keyboard and it looks like this. So this hopefully gives you an idea about how abstract and how new these quantum computing systems look like. This was actually an April Fool's joke by the IBM team to say, okay, if you're looking for the keyboard, don't. You know, this is a system that will be embedded within sort of normal computing systems. So, you know, it will probably run alongside a normal computer. And for the people on the outside who like to know where the keyboard is, you probably won't notice anything different. You'll probably program it in the same way. But for the people working on the inside, sort of familiar with the hardware, you might notice this quantum processor, quantum coprocessor, which just works to speed up certain types of problems and things like this. So that's sort of what quantum computing looks like from the outside, in terms of sort of how you might access it. And in terms of business models and things like this, there are obviously lots of systems nowadays are run on the cloud. And in fact, you might not know, but in fact, a lot of people really at the cutting edge of things like artificial intelligence, machine learning, big data, people crunching huge data sets are increasingly looking for novel and pretty esoteric new platforms which just give that slight performance improvement that helps them crunch their numbers slightly faster, when in fact, otherwise they might just not have enough time or resources to solve. So the industry is moving towards new computing platforms. And in fact, from an engineering perspective, maybe all of this stuff will never be seen by users, by the outside environment. But that's what it looks like for those involved, interested. So from the market perspective, I think I've probably given too much away already. People are looking at this as a new era of computing. And I will admit some of this is slightly overhyped. There was a report by McKinsey that suggested that this would be $1 trillion market by 2030. Maybe I think that's slightly ambitious in terms of the timescales. I am a strong believer in the fact that if you start developing an emerging technology, even though you might not know where it'll end up, if you have a neat idea about where it will go in the short term, the long term may well very much lead to very much longer term benefits, which may end up being as valuable as $1 trillion as McKinsey have suggested. But if you look under the hood about why people think that it might be $1 trillion market, you start to see some quite interesting trends. So if you look at the computing industry, you do see lots of very, very high-end mathematical and computational problems that people are trying to solve on classical normal computers. But essentially they run out of computing power. So you might imagine, for those of you who've ever tried to do computational fluid dynamics, so try to program airflow or something like that in a finite element model or something like this. Everyone knows that at a certain point your computer just runs out of memory, runs out of processing power. And essentially that's because at some point there are so many parallel processing, there's so much parallel processing that's trying to be, that's attempted, that eventually the problem just becomes too large for any computer. And there are certain problems where it's believed that no matter how much you increase the size of your computer, classical computer, the problem will always be too large. So some problems, I guess another way to say it is some problems are just naturally not suited to the sort of pretty binary approach, pretty sequential approach that classical computers take. And to give you some ideas what those problems are, probably a lot of the audience here have tried to solve differential equations. Those are quite challenging to solve, especially when they get large in classical computer. Linear algebra, computational optimization. These things may not mean much to this audience, but they're essentially trying to say lots of mathematical things, operations, which current computers are very poor and very slow and inefficient at solving. And those problems actually do have a lot of relevance across different industries. So a nice example is drug discovery. So increasingly, pharmaceutical industries are trying to model how drugs behave purely in silico inside of computing systems. And imagine how large and complex a drug might become. That quite quickly becomes sort of impossible to model as completely in a normal computing system. And then even more practical things like modeling of physical systems, financial markets, for example, computational fluid dynamics. You get to a point with many of these models where the number of different parameters makes the size of the computational problem too large to try and tackle in a normal computer and logistics. So hopefully I'm helping to explain how normal computers and huge data centers and things like this might seem incredibly advanced, but in fact still are not good enough to solve some problems that real companies are trying to address. And And a slightly different view, actually, which was presented to us by one of our advisors within Orca. So one of our advisors has just come to us from the Cray, who were a world-leading provider of high-performance computing servers. So basically, lots and lots of servers. And this guy said to us that Cray were very worried and concerned about the energy efficiency and the energy use involved in computing. And there are some nice statistics. So the amount of energy that's used to train an artificial intelligence algorithm is actually very high, and is actually a major hurdle for lots of companies to address if they're looking to get into that. So the amount of energy has doubled every 24 months since 2006. And you're now at the point where our advisor joked with us that at one point Cray thought that the only solution would be to provide a nuclear reactor alongside these huge data servers that they were providing to their customers. And this is hopefully explaining why Google and companies like this are interested in putting their servers in the Arctic on ships. It's purely because of the huge amount of energy that's required in running these massive calculations, and that is only going to get worse. So from just an energy point of view and an energy efficiency point of view, there's a need for a new technology. So what about quantum? Why is quantum so interesting? Well, if you look at the amount of sort of computational resource available to you and how that scales with the number of qubits. Qubit is a quantum bit. So when you have just a few qubits, every time you add a new qubit to your system, because of the way the quantum physics works, you essentially double the size of your quantum state available to you. And I guess imagine, people like to describe this a bit like a maze. So, a classical computer will go into a maze to try and find the quickest route towards the center. And a classical computer will basically try lots of different approaches, which you can sort of see sort of works if you have a small enough maze. But a quantum computer, because of the way it works, because of the way it involves this way to model very parallel systems, a quantum computer can actually try and contain within a single computation every route within the maze that you would possibly take. So imagine each qubit allows you the possibility to pick a direction, but within a quantum computer, you're able to pick both directions. And through that mechanism, hopefully you can see that a quantum system can hold, as you increase the number of qubits, a very much larger computational state, a computational resource than a classical computer. So that by the time you get to something like 300 qubits, which is the point at which people generally believe that a quantum computer will be able to outperform a classical computer. It's obvious why, because the equivalent number of classical bits that you need to model that quantum system is something like 2 × 10 to the 90 bits. So way beyond our current capabilities. So that's part of the reason, that's pretty much the reason in sort of non-technical sort of language why these computing systems are believed to be so powerful. And of course it goes beyond that. So at 301 qubits, you'd have double the size of the resource, and it goes on from there. And to give a slightly different picture, I like the slightly more physically intuitive picture. I said to you earlier that quantum computers are thought to be able to provide the answer to drug modeling, the modeling of new drugs and new pharmaceuticals. And maybe the reason why you need a quantum computer to answer those problems is maybe clear. So imagine, you're a computer scientist and one day someone puts this very complex system in front of you. So for those non-chemists, I'm sure everyone knows what this is, but the dots represent atoms and the links represent bonds and the little spirals represent complex molecules. So as a physicist or as a computer scientist, what you need to do is say, okay, sorry, this is the only bit of maths I'll have, but imagine each atom, we need to describe that as a matrix. So a data array, which describes all of the parameters of just each atom. So each dot there would need to be represented by a matrix, which is the sort of the little array thing in the middle of the screen. But that's only the starting point. So if each atom is represented by one matrix, well, you've got thousands of atoms in each molecule. So in fact, what you need to do is have a matrix of of matrices or a network of matrices. And that is something like it's shown in conceptual form on the right-hand side. So each dot there, if you're hanging with me in sort of abstract space, each dot there represents a matrix, or in fact a tensor, a multidimensional matrix. But because of the sheer complexity of this problem you're trying to solve, you actually need to have a network of tensors. And if any of you are following me at this point, then good. If you're not, just imagine just a hugely, massively networked just data set. And if the classic problem, if you try and move one atom to see how it affects the rest of the system, everything changes. So everything is interdependent, and therefore nothing, your model is very hard to find a ground state. So when you're doing this, what you really want to do as a computational scientist is find the lowest energy ground state of that molecule. But obviously that lowest energy ground state relies on finding one configuration of all of those atoms where the energy is minimized. Okay, and to complete the picture, what is attractive about a quantum system is, although I'm not going to suggest you can build a quantum system that will solve this just yet, where we are right now with quantum systems is you can build quantum circuits, quantum devices, which naturally can contain the same complexity that would be found in that drug molecule. So what we like to think is we can design this novel degree of circuits, which, although at the moment, the state of the industry is we can't form that link. You have two quantum objects. You have the drug, which is a naturally complex and quantum object, and you have your specific bespoke piece of hardware you've built, which is naturally also complicated and quantum. And it's sort of a case of building yourself some operators within the quantum system you've built that can naturally optimize and optimize your natural system. So without seeing you, I can't tell if I'm completely losing you or not. You've got one quantum system mapping onto another quantum system. So the best way to model a quantum system like a molecule is probably with a quantum system as a machine. Okay, so let's go back a little bit and say, what really is a quantum computer and why are they so challenging? So one reason why quantum computers are so, and pretty much probably I would say the perfect and most challenging engineering challenge you could imagine right now, is because in order to build a quantum system, you essentially need two contradicting parameters, two contradicting characteristics. So the first thing you need to do is you need to have a completely isolated system. So you need to have a system where you just set something up, you set a state up, you imprint some data on it, and it just stays that way for as long as you need your calculation to last for. So imagine, and people, as we'll get onto in a minute, people use single ions, so people use single photons, people use single electrons. But the important point is when you're trying to manipulate these very fundamental and simple particles, they should not interact with at all the outside environment. So your ion has to be in a very low vacuum so that there's no collisions with outside gas. Your single photon has to have no chance of being scattered, and your single electron needs to be in a superconducting state so it just stays as an electron without being interfered with the outside environment. That is all sort of good, and you can do that, but the challenge is that what you also need to do is have that very isolated object. You need to be able to control and couple to that isolated object. So you need to be able to say to your electron, okay, in certain very well-controlled ways, I need to apply a very well-controlled voltage to you to change the spin on my electron or something like this. But it should be in a very well-controlled way that only changes the energy state of that object by an incredibly well-defined way. So anyway, I like to describe this as sort of the contradiction of being isolated. So you're at one point you're on your own on a beach, but at the same time, sometimes you need to be able to bring qubits together and control their interaction in a very well-controlled way. And that is the perfect contradiction of quantum systems, which makes them so challenging. How are people looking to do this? So what does the general industry look like? So I'll cover just quickly two of the main approaches, superconducting systems and single ion systems. So in a superconducting system, you have a superconducting circuit, or what's called a Josephine junction, where essentially if you apply a small amount of current to this system, because it's a superconducting system, then the current just keeps circulating in a loop forever. So it keeps going round and round until you apply your very well control, your very precise control field, in which case you can change the current so it starts circulating in the other direction. So that's the isolation. The current keeps circulating in it forever, but then you're able to also apply a very well-controlled pulse of microwaves in order to get your electrons circulating in the other way. And there's lots of circuitry that goes around that circuit in order to apply microwaves. And this audience, I guess, being based in Essex, is probably very familiar with very high-end microwaves. You essentially control that spin of the superconducting circuit with microwave fields, and so it's the microwaves that apply that very careful control. Now, the challenge with these superconducting circuits is when you need to build up more than one of them. So one is fine on its own, but as you start to build in more and more of these circuits, you need for them to be independent from each other. And effectively, the problem becomes is that there is a lot of unintended coupling between these circuits. So what you want is for each one to be completely independent of each other. But as sort of the audience might know, if your circuits can be coupled through microwaves, it's quite hard to stop that from happening. So what a lot of the community are facing is the problem where if you want to just control one of these qubits, you actually inadvertently also affect all of the other ones. And that makes controlling your programming quite hard. And this is sort of a nice graph that just shows what happens if you try and just control one qubit, you in fact end up inadvertently applying a signal to all of the others, which as good engineers is very difficult to control. That's superconducting quantum systems. Another approach towards quantum computing is using single ions. So imagine single atoms, and you strip off an atom, strip off an electron associated with that ion, and it leaves you, strip off an electron from the atom, and it leaves you with a single ion. And then what people have done, which is really neat, is you're able to apply electromagnetic fields to trap those single ions in place. So you can see in the picture here, you've got lots of electric nodes which produce an electric potential that you then sort of switch backwards and forwards very quickly in order to sort of trap your ions in a very precise place. And what's neat about those things is essentially imagine your ion is then independent. That suits your isolation criteria. So your ion sort of is on its own. And then in order to couple these things together, you can change the potential to bring ions together. So that's ion-based quantum computing. And I guess maybe if to give a slightly different perspective, if all of you are wondering, what if I'm talking about, I guess something I should have said at the start is that essentially quantum systems are essentially simple harmonic oscillators. So what you do is quantum is sort of the theory that treats all of these isolated systems as waves. And so what you're trying to do as a wave, you're trying to set up just this simple harmonic oscillation in each of your objects. So each of your objects is sort of like a pendulum that's swinging, and that swinging represents the data. And then what you want to do to build up a computer is be able to couple those pendulums together. So couple your simple harmonic oscillators together. And eventually, hopefully you sort of realize that as the number of items that are coupled together grows, your eventual state is then dependent on lots of these simple harmonic oscillators, which is quite a complicated problem to model. So that's what we're trying to do here with the superconducting qubits and the ion-based qubits. And this is what they look like in real life. So you get lots of chips, lots of silicon or sort of slightly different other material chips. So a lot of the stuff is silicon, where you just, well, in the case of superconducting, you have a superconducting material that's sort of etched in a particular way to carry your current. And those superconducting systems are being very heavily backed by the big guys like Google, have a program like IBM and some other startups. You also have, in the trapped ion space, you have some big players like Honeywell, so big American defense company, really pushing quantum computing, but in their case with trapped ions. So that picture in front of you is a fabricated silicon chip that contains all of the electrodes that traps those single ions. And what you can't see is all of that's contained within a very low vacuum chamber system. And then you start getting these other approaches, like I'll talk to you in a bit more detail, related to single photons. And so you get these people who look to contain single photons, single units of light in wafers of silicon and perform quantum computing that way. So if some of you have heard some of the news stories come out recently, there have been a few in the Financial Times and Economist and things like this, sort of presenting quantum computing being here and now, and you better get on board and start using your quantum computer. It's not quite the case that that's true. So at the moment, there is a bit of an arms race on between these huge players and lots of startups to be the first player who can essentially grow your quantum computer to a size, to a number of qubits where you can perform useful computation. So currently, the world leading record is something like 53 qubits from Google. But as I said before, you need to get to a point where you need 300 qubits before you can perform useful computation. So there's a way to go. And what's neat from my perspective and the UK's perspective and lots of other startups is there's lots of room for new approaches and new innovation to basically bridge the gap and get from 53 qubits to a few hundred where these systems are useful. So I like to say to people about this thing called I call the quantum gap. So you have lots of hardware providers pushing out platforms that will carry this quantum information. And surprisingly, you have lots of software companies. So people looking to design computer programs that will use quantum systems. So basically, like I said at the start, redesigning what they think computing looks like, redesigning how they're coding these machines to run these quantum systems. And lots of end users, so lots of big corporates, Airbus and BT, AT&T, Goldman Sachs, big banks, all sort of trying to get an angle, trying to start working with quantum systems so that they can start understanding how they as a business will take advantage of this huge power. But unlike maybe some of the press releases, there is this outstanding technical and I would say engineering challenge in getting from those small numbers of qubits to a system which can actually run the type of software that people are running. So there's lots of parameters. I think I've mentioned already the number of qubits, so the number of these objects that people can create without it sort of being swamped by noise needs improving. But also some things like the gate fidelity, so the quality at which you can apply operations on these systems is currently too low. So you can build a system up, but as you start to perform operations, gates or computational processes on the systems, there's so much noise associated with the way you're operating on your system that eventually you're again swamped by noise. There's a lot of challenges related to the connectivity. These systems need this quantum connectivity between them to work. And again, that presents a challenge in terms of the amount of connectivity that you can introduce without noise swamping. And then maybe some things that feel more natural to this audience, the systems aren't fast enough currently. They're quite slow. They're certainly not up to the speeds of your gigahertz processor in your computer. There's certainly not enough attention or not enough activity working out how you actually manufacture these devices at scale. And then there's an increasing need for integration. So a lot of even the big players, Google and IBM, they're very much treating their quantum computers as isolated computing systems. But as all engineers know, these systems will need to be embedded and integrated within other computing systems. So there's a huge integration challenge associated with that, bringing a quantum computer in to be connected with a normal computing system. And as engineers, you'll appreciate, we've had some conversations with data center owners where they said, okay, here are our set of requirements for getting a quantum system into our data server. Do you meet these requirements? And a quantum system until now is largely not focused at all on whether those requirements are being met or not. And then, of course, the Holy Grail. A lot of people in quantum think that it's so important that it doesn't cost benefit, doesn't matter. But these systems are very scientific, very complex, and are very expensive. So how much those systems can be made to be commercially viable is another question. Okay, so now to take a slightly different tack. So Orca computing has very much sprung up on the belief that we think that those other platforms are going to struggle to scale to large numbers of qubits. So our approach so far has been to well, design and to push a completely new approach towards quantum computing that's based on single photons. So single photons, imagine light, a laser beam, is comprised of, the fundamental unit of light is a photon. So imagine the equivalent of electricity and the electron with light is a light and a photon. So you're talking about very tiny units of light. And why do we think photonics are important for quantum computing? Well, because photonics is already used to carry all of the information that we rely on for that underpins the internet. So the reason why the internet works is because you can send in a laser pulse on one side of the Atlantic, and on the other side of the Atlantic, it comes out, pretty much unperturbed with a bit of amplification. So light and optical fibers are a very robust platform to noise, and that actually naturally makes them quite good carriers of quantum information, where you want to just encode. It gives you your isolation that I talked about in my previous slide. But one of the key challenges trying to do computing or quantum computing with single photons is photons just inherently don't interact with each other. So one of the reasons why they are so robust against the environment, if you do put a single photon into an optical fiber, that it just carries on containing the same state or the same information that you put in there in the first place, is that just photons don't interact with many things very much. And my co-founder likes to describe this as the sort of Star Wars picture. If you watch Star Wars, you know that lightsabers, you've got Darth Vader and Luke Skywalker with their lightsabers that bounce off each other. Us in the photonic space sort of see this as a bit of a joke because, if that fight was to happen in real life, photons don't interact. So those lightsabers would just pass through each other. So there'd be like two torches just waved at each other and there'd be relatively no interaction. So essentially trying to build up a quantum system that relies on two single photons interacting with each other and becoming correlated, becoming entangled, actually doesn't work very easily, because typically these two photons just pass straight through each other. But the lucky thing is with photonics is that actually photons do interact with each other. But just the problem is that they just don't do that very often. So if you send two photons at each other, they will interact and they will couple, but the problem is that's just quite an unlikely event. So the answer to all of our problems is this thing called heralding. And that's essentially a thing that says that the nice thing about photonics is when these two photons do interact, they actually always produce a characteristic signature that tells you that the two photons have interacted. So with all of, and I'll come on to more concrete examples in just a minute, but they're essentially this, if you're trying to interact two photons, it's a bit like CERN, the sort of nuclear reactor. You always get this signature that's created if your two photons have interacted with each other to tell you that that operation has been successful. So within Orca, we've been sort of working on these ways to make use of that that nice herald, that nice signature that you get. And so to give you an idea, so this is a system that we use to produce single photons. So even that in itself is very hard. So typical light contains many billions and billions of photons. So just creating one single photon is actually quite a challenge. The way we do that is we pass a big pump laser beam into a particular device, a crystal, that essentially takes one very high energy photon and turns it into two photons of a lower energy. So that operation works. It's quite well known in labs, but the problem is that it's only likely to be successful 10% of the time. So you don't want a photon to produce 10% of the time. You want a photon to be produced 100% of the time. So what you can do, in fact, in your system, is you can rely on this fact that because you produce two photons, one of those photons can give you this herald, this idea, this signature that you've generated this single photon event. And what I'll come on to describe in a little bit later is what you can do then is you can then use that to overcome this sort of randomness problem. And not to get into too much of the details, you can also do that with entangled photons, which is our coupled system when we're trying to couple systems together. So when you're trying to get two photons to interact with each other, and sorry about the diagram, it doesn't make much sense. It's an interferometer for people in the know. Essentially, your two photons don't interact most of the time, but sometimes they do. And what's nice and what this picture is sort of illustrating, or should illustrate, is when those two photons do interact, you produce a really characteristic signal that tells you that they've interacted. So again, you get something which is not 100% certain to be successful. That would be a problem, but you're always able to generate this herald, this signature that tells you that something has been successful. And then to complete the loop, oh, sorry, that shouldn't have skipped. So to complete the loop, what does all that mean? Well, essentially in our quantum systems, it allows you to do buffering operations. So even though, so on the left-hand side, you've got events that are random. So the event at one time, there's a certain chance that they might be successful, but you can use this herald, this signature, to inform you that your event has been successful. And then, like a lot of physical systems or computational systems, you can then rely on a memory element to act as a little buffer. So your herald will tell your memory to say, okay, that event has been successful. Hold that successful event in memory until we're ready for you. So you can essentially increase the probability that your event has been successful by sacrificing bandwidth. So you can allow your clock speed to run slower because your whole system is buffering to allow for these operations to happen. So I'll maybe move on quickly. I've taken up a long time. So some of the things that I'll show you now are just on us implementing our system. So we have started demonstrating in terms of what the physical thing actually looks like. We're storing single photons within a vapor gas. So in our case, a rubidium vapor gas. So I hope you'll be able to appreciate the sort of engineering challenge in doing this. So you're taking one single photon, which you can only just about detect with a silicon detector or a normal photodetector, but just about, so the tiniest unit of light you can imagine, and you're able to store that within a gas and then retrieve it later in a way that acts as a memory element. So there are lots of laser systems that go into our devices, and really here you can see the core element, which is a vapor cell, which is being controlled in a very particular way with certain light laser fields to be able to capture just that tiny single photon. And there's a bit of the details. So, it revolves a 2 photon absorption, but to be honest, for this audience, unless there are any questions, I won't get into that. And maybe one of the last slides I'll show is just, what does all this mean? If you're sitting there wondering how on earth this can be used for computing, this is what the system looks like in schematic format. So essentially what you do is you start off by generating single photons, so single qubits, so single little objects that carry a piece of information. And then what we do is we rely on these coupling processes, these entanglement processes, to basically fuse the properties of those single photons together. And that essentially is your computational resource. So it does get very abstract at this point, and to be honest, I don't understand the full extent of it. But once you've got this very highly coupled state, so lots of single photons that are all interdependent on each other, there are operations that you can do, that you do, and in our case with photodetectors, to control that state in a way, and hopefully to give you an intuitive picture, to allow the state, this physical object, highly correlated physical object, that allow that physical object to evolve in time and maybe to explore sort of parameter spaces and perform computation, which you could not do with a classical computer. So that's what, in abstract form, the system looks like. You take single photons, you entangle them together, and then you use that entangled state to perform physical processes that in abstract land work out as computational processes. But maybe this is familiar to this audience. This is just stuff that happens inside a classical computer. but just we're sort of reinventing it for a new platform. And I'm approaching the end. There's a lot to give you an idea of how complex this system will become. Eventually you do need thousands of qubits, quantum bits. So we have this sort of roadmap that starts with the thing I've described, the quantum memory, but pretty quickly ends up becoming very abstract and very complex, which is the fault tolerant lattice. So this thing that describes the state you're creating in the bottom right. And if there are any systems engineers in the audience, of course, this is probably, you're probably very much in tune, and you'll understand that systems engineering is the thing that will lead to this object being understood, because by the time where this object on the bottom right hand side reaches the market, no one is going to be worried about what's going on with the single photon. It'll all be abstracted out. It'll be a black box and understood from a sort of systems engineering point with a higher architecture. And the last point I'll leave you with, just in case there are any sort of error correction sort of people or network engineers in the audience, in terms of the way these systems run, the full roadmap requires this thing called fault tolerance, which is what your computer has. If you have a bit in your computer that's supposed to be, carrying a 1, there are lots of processes built into your computer where, if just natural effects, if you drop your computer and a bit flips from a 1 to a 0 because of noise, there are systems in your computer that will correct for that and turn it back into a 1 like it should be. So within the quantum computing space, there's a lot of work happening on that as well. And in our case, you can think of it a lot like a sort of a very large network, where in that network you can afford to drop certain links. So the gray objects are certain links that you might drop, but overall the network as a whole remains connected and remains functional in a way that you can later go back and correct for that. So there we are. That was pretty much my last slide. This is us as a team. If you want to focus on the startup side of things, we're a company that formed in November. It's been a really exciting journey. We've already grown to a team of 10 people, and we've secured 3.1 million pounds of investment to build this out. And I'm lucky enough to work with a bunch of really talented people, and included in that is Professor Ian Walmsley, who's also Provost of Imperial College. So there's a lot I could say, about startup culture and the way you grow a company, but maybe I'll leave that if people are interested for the questions and answers. So with that, I'll say thanks very much for your time. As I say to everyone, if you are interested for this audience, we are hiring different people, so let me know. But please, I'm sorry if that was too much. I hope there are good questions. I hope I haven't lost you.